Hello all. So in this video we are going to discuss about the XNOR gate implementation using XNOR and as well as the XOR implementation using NOR gates. Okay. So in previous video we have discussed about that XOR and XNOR implementation using NAND gate. So now we'll just try to implement using NOR gate. Okay. So if in case of NAND gate we have just started with the XOR gate, so here we'll just start from XNOR gate. Okay, XNOR gate implementation using NOR gate. Okay, that is the one we'll just start with. So yeah, as we already know, right, it won't be same like it won't be simple as that as a basic gates. Okay, so here we have to do something different when compared to the basic gates. So as a traditional method, we'll just start with the truth table. Okay, so we'll try to do with the truth table first. If it is not, we can just go with another technique. So okay, how to write the truth table, that and all, yeah, you could refer the previous videos for that. So the XNOR gate for this one, so what we will be having like this, and for NOR we will be having like this. Okay, so this is for the truth table of the one. Truth table of the gates, which are all like one which we are going to implement, and the one another is that which we are using to implement that one. So this is the truth table of both of that one. So from this, currently what we have, this is what we have. Okay, so this is the NOR gate, that is what we have currently in our hand. So we have to convert this, we have to implement particular this functionality only using this gate. So you don't have any other gates in your hand, you have only this. So with this you have to implement this. So okay, we'll try to compare the outputs. Okay, so generally if we compare the outputs only, we come to know, right, we can just okay, the outputs are somewhat correlated, so we can able to produce this particular implement gate with implement with this particular gate. So that's like something we can able to come to the conclusion if we have some correlation between the outputs of this particular input combination. But if you see here, right, here it is three high we are seeing, and here we are seeing only 2 high. So there is no direct correlation between the two outputs of the two gates. So okay, so here, so we come to know directly we can't able to implement the XNOR gate using NOR gate. Okay, this is not as straightforward as we think. Okay, then which method we can go? Okay, after truth table we have one another term, that expression, right? So for every gate we will be writing some expression. So for XNOR, our expression, how it looks like, it will be AB plus A bar B bar. So how to write expression for this one also, we have a previous video, so you can refer that. So this is what about the XNOR gate which we are going to implement, and this is NOR gate, that is we have already as a, this is the ready-made cell we have. Okay, so these two things we have to think. So this is the gate we are going to implement, and this is the gate we are going to use. So these are all the two expression of the particular gates. So among this AB plus A bar B bar we have for this particular XOR gate. So consider if you see this one, right, if you see the expression of the NOR gate, A plus B the whole bar. Okay, if I divided that into the this one, like if I divide it, it will be A bar dot B bar 1. But yeah, this is about the NOR gate. So definitely we will be having only the NOR gates. So instead of going from the forward side, right, from the input to output, we'll just try to implement this with from the output side. Then only, because we know output will be having only one output, and that too we know what is the output we know. So if we have to we have one gate, that's output we know, then only then we can just be able to predict the inputs of the gates, right? So that is what the approach we are going to follow here to implement the XNOR gate. So okay, we'll start from the final NOR gate, the output NOR gate will start. Okay, so here if you see A plus B the whole bar will be equal to A bar B bar, this thing. But what we have to implement is this one, AB plus A bar B bar. So if you see, it is not in the form of NOR gate, right? It is just a OR gate. It is in the format of OR gate. So with this we can't if even though if it is a product form, right, so we can do something like double bar. If we do, it will become an OR format, so that we can use directly. But since if it is an OR form, if I put another one bar here, again it will become, it won't become NOR. You got it, right? So it will become NAND only, it won't become NOR. So the double inversion won't work here. Okay, so what we can do, we know, right, XNOR is a XOR plus NOT. So at the output side we will be adding the inverter at the XOR gate, it will become the XNOR gate. That is what we know. So what it could be in the NOR format, if I have to do means, I could do like this, right? A bar B plus AB bar the whole bar. Here the A bar B plus AB bar is what? That XOR gate. So XOR gate is this, and again I am at the output I am putting that inverter. So XOR plus NOT I am going to use to my implementation. This is because to make it as a to view this as a NOR format. Okay, so because I am going to use only the NOR gate. So this is what I got. So now what I have to implement, A bar B plus AB bar the whole bar is the circuit I want to implement. Okay, for this first we'll draw our final NOR gate. Okay, final NOR gate will just draw. So if you see this is the NOR at the out, this is A exclusive NOR B. This is what it will be. So for this what we are expecting, for this input terminal what we are expecting, if you see this particular one, so A bar B is one thing and AB bar that is getting ORed and NOT. So this is an OR operation. So we need A bar B in one place and we need AB bar at one place. Okay, this is what we need. If I give these two, A bar B and AB bar at the input terminal of this one, the output I will be getting my XNOR gate. There is no other issues with that. Okay, this is what how the first NOR gate we have implemented. Okay, now this A bar and B and AB bar we know we have to do, right? So the A bar, okay, as maybe you can think that the A bar and B bar we can just have a different this one, right? That is what is that? One different NOR gate for implement the inversion operation. Then we can do this one. But if that is the case, if we want to do something like that, it will be extra one gate will be there. So I'll tell you the optimized method first. Then maybe we can implement using that method also. Okay. So this is the A bar B and this is AB bar. Then okay, we need A bar B. So if as we already we are discussing, A bar B is in the product form, right? So we need it in a NOR form again. So yes, so we need it in a NOR form, right? So currently it's a bar B. So what we can do, we could have same like demarcant theorem, right? Double inversion will do, and based on that we'll convert it to some of the that format. Okay, so the NOR format. So here if you see the A bar B, then what we are going to do now, double inversion will do to make this as a NOR form. Okay, so A bar, it will break the bars, right? So A bar the bar plus it will change the operator in between that and B bar. Okay, the whole bar is already there. So how it will be, as we know, right, double inversion will be like it won't change the functionality of that. So it will be A plus B bar the whole bar. Okay, so this is the one format we get to generate this A bar B. Okay, so this is like this NOR gate we will be having this A plus B bar the whole bar to make this one. And okay, same as that for AB bar we'll convert it into NOR format. Okay, so how it will be, AB bar the double inversion, then we will converting this, it will be A bar plus B the whole bar. Okay, A bar plus B bar the bar, yeah, B bar the bar, then again we will be having the B only, so the double inversion. So A bar plus B the whole bar. So we got the next level of that NOR gate. Okay, so this is the NOR gate. So it is giving to this one, and this is one another NOR gate. This will be driving this one. So for these, what we need, one input we need a A and one input we need a B bar. So here also one input we need B and one input we need A bar. This is what the expectation here, right? So if you see, this will become this NOR gate, so it will output this one, and it will output this one. Okay, now then we have to find out here what and all the ready-made inputs we have currently. So the A and B are the ready-made inputs that we have, and A bar B bar are not ready-made inputs. So if we have to make A bar and B bar again using an OR gate, means again we need extra 2 gates, right? So for B bar 1 gate and A bar 1 gate, so it will be 5 gates. But we are trying to implement this as an optimized design. So we will do some more analysis here. So okay, consider we need instead of this bar, you just ignore this bar and you need A plus B bar. Okay, the whole bar is there, right? So this whole bar we have. So here something this like only, right? This format, NOR format, this will be the A plus B the whole bar, B bar the whole bar, and here it will be A bar plus B bar the whole bar. So consider this as a OR gate and ignore this inverter as the expression in both the places, expression as well as the gate. Okay, so now we have to implement A plus B bar using OR gate, right? So we have a we have to actually this A plus B bar we have to give it in the 2 terminals, A and plus B bar, then only it will be generating this, right? So what I am trying to tell here, consider this B bar, A already we have, so this B bar only we need to have. So what I am trying to tell here, we have to, because we have here only 2 format, right? So we have to add certain things just to make this particular B bar to disappear, or maybe different particular product form, something like that. Okay, that will be like just with only one NOR gate, and that will output here and here, and it won't make any other things. Okay, so because why I am trying to tell, we are trying to do this one, this is because if we have done like this, it will be like one more gate, it has been the reduced gates. Okay, so now this B bar we need, right? So the B bar, okay, here we need the B bar and here we need the A bar. Okay, so this is what we need. So as we know, like how we can come to the conclusion is like, okay, one thing is there. So that is something like we have like this, right? This some of the properties. So some things won't change the functionality of that. Along with that, we can add some of the thing. What I'm trying to tell, okay, I'll tell you some properties, but about that we'll discuss later. Okay. So if I have A plus A bar B, this is some other property. For to prove this property, I will provide you the different session. So but here we'll just try to use this property alone, right? So this A plus A bar B will be A plus B, and yes, yeah, A plus A bar into anything. If it is X, it will be A plus X. Okay. So this is one property. I'll just explain this in a different video. This will take some more explanation needed. So I'll explain this in a different video. Okay. So the A plus A bar B will be A plus B. Okay. And A plus, yeah, anything we can do. So what I'm trying to tell, if instead of A plus B bar, we can write it as A plus A bar into B bar. And here same like that. Okay. A bar plus B. So this A bar plus B, we can write it as A bar plus B plus A bar B bar. Okay, so now you come to know, right? So what I am trying to tell you, so instead of A and B bar to give the NAND gate, we can have like A plus here and here A bar B bar, and here also A B, and here it is A bar B bar. Got it right? So A bar B bar, instead of B bar we can have A bar also, it won't change the functionality. Here also instead of B bar we can have A bar also, it won't change the functionality, because these are all like A and A bar, so B and B bar here, and here A and A bar will be the inverted versions, so it won't affect anything at the output side, or here also it won't. Okay, and now what we need, A bar B bar, A bar B bar and A bar B bar here. So A bar B bar, as per the De Morgan's theorem, if we convert the bars, that broken bars into the single bar, means how it will become the whole bar, and here since it's a product term, here we can have it as plus. So it will be A and it will be B. So now with only 4 gates we have implemented our XNOR gate. I think it's clear to you. Let's this is about the XNOR gate implementation using NOR gate. Okay, so I think you are clear. So we'll just same as that, right? So now if we want to implement the XOR gate using NOR, what we can do, same as this one, XNOR followed by one NOT gate. Okay, here it will be A XOR B. So here it is the same as this will be same as this one, and this one we can just add one NOT gate at the output. So 5 gates will be needed for XOR, and 5 NOR gate will be needed for XOR, and 4 NOR gates will be needed for XNOR.